Alright, in this video I'm going to be explaining induction, how to write a proof by induction, and I'm going to try to focus a little bit more on how it actually works rather than doing a complicated example or anything like that. But to start off, let's just introduce something that we can prove by induction and then work with it a little bit and show how, the idea generalizes to any other case where you can use induction. So a pretty common example when induction is introduced is proving the statement, which we will call P of n, that the sum of the first n terms is equal to n times n plus 1 over 2. And if you try this with, just a few numbers, you'll see that, it'll work out. But we want to show that it's true for all the natural numbers. And you can't show that just by plugging in as many numbers as you can because, you can always plug in the next natural number. So induction helps prove that something is true for, all natural numbers past some threshold. In this case, we're trying to prove that it's true for all the natural numbers. So we start at 1 as kind of our starting point. And when I say starting point, that brings me to the next idea, which is the base case, which is usually how you start off a proof by induction. So start off, we say base case, and the base case is going to be one case where you prove that the statement is true by hand. So we can look back at our statement and let's say let n equals 1. So we're considering the sum of the first 1 terms. And of course, that's just going to be 1, and this equals 1 times 1 plus 1 over 2, which is 1 plugged in to this up here. And then we get is equal to 1. So P of 1 holds true. So we get one case where we can show that this works, and we're not concerned about all the numbers yet. We're just showing that it works for one of them, and this is going to be kind of the ground for our argument. And we will build it up using the inductive step, or the inductive hypothesis and the inductive step. And I should add up here, we want to show that this is true for all the natural numbers, right? So this is the goal. So we have our base case where we have shown that it works for n equals 1, and we're going to do the inductive step next. So the inductive step includes the inductive hypothesis, which is basically the following statement, where we assume P of k to be true for some natural number, or some k, that's a natural number. And we want to consider P of k plus 1. Now, if you have received any instruction about induction before, it's pretty common that it's explained as kind of a domino effect. And this is what we're going to be seeing in the following step, where basically what we're doing is we're showing that it works for one case, and if we can show that it works for this one case, and under the assumption it works for this one case, the next case works, then you have another case that works, and then you can plug that back in and repeat the process. And that might not make sense just in words, but hopefully that'll make a little more sense once I start actually working out the example here. So if we're considering P of k plus 1, then we're going to think of the sum of the first k plus 1 terms. So we have 1 plus 2 plus up to k, and then plus k plus 1. And before I move further with this, I should note that P of k plus 1, we want to show that we can represent it in the previous form up here. So if we plug in k plus 1 as n, we get k plus 1 times k plus 1 plus 1 over 2. This is k plus 2 over 2. So this is what we want to show we can build, Because if we can build this under the assumption that the previous term is true, we know that whenever we have a term where P of n works, then it works for the next term. And then we know that it works for this term now, so then we can do it for the term after that, and that's where the domino effect kind of happens, right? But we're working under the assumption that P of k is true, and since we're doing that, we can substitute the sum of the first k terms as k times k plus 1 over 2, because we are assuming it to be true, so we are allowed to make this exchange up here. Now, we have the plus k plus 1, and then we can distribute that k. We get k squared plus k over 2 plus k plus 1. And then we want to get that k plus 1 over the 2 as well. So we can multiply both of those by 2 and get them like this. We have k squared plus k plus 2k plus 2 over 2. Further simplifies to k squared plus 3k plus 2 over 2. And you can factor that and get k plus 1 times k plus 2 over 2, which is exactly what we were looking for. These equal. So we have shown that you can represent the k plus 1 term in the form that we were hoping for under the assumption that P of k is true. So we know it works for k plus 1. Now that we know it works for k plus 1, you can consider k plus 1 as the P of k term, right? Or that might not be the best way to say it, but we just know that it's another case where it works. And since we have shown from the step here, if we assume something to be true, then we know that we can build the next term. So we have something that's true, and then we can build the term after k plus 1 in the desired representation. So that's kind of what's going on here. And since we're starting at a case where it works, n equals 1, we can build it for the rest of the terms in the natural numbers. So by induction, we have shown that P of n is true for all the natural numbers. So just like that, we have now shown that the statement we have up here, P of n, holds true for all the natural numbers.